Hello everyone. Maybe looking around you, especially in nature or seeing pictures of animals, you have wondered why certain shapes, certain patterns keep coming back. Why are honeycombs shaped like perfect hexagons? And so are snowflakes, basalt columns, the compound eyes of insects, or the plates on turtle shells. Why this hexagonal shape rather than squares, which are far rarer in nature? Not absent, for example, some mineral crystals are naturally cubic, but there are few natural squares. And this is just an example. Some patterns seem to form repeatedly in the universe, on very small to very big scales. Patterns like spirals, from plants and the shells of mollusks to galaxies, waves, cracks, stripes, symmetries, while other possible shapes, geometric or others, don't occur much naturally. This is the question we are going to examine tonight. Why do certain shapes appear instead of others, or chaos, no shape at all? This topic gives an opportunity to at the same time wonder at the beauty and creativity of nature, and also understand it a bit better. We will see why certain shapes and patterns occur, and others not so much, which will take us to various disciplines: physics and chemistry, mathematics, biology, also art and our sense of aesthetic. It opens many other doors too, on things such as the Fibonacci sequence or the golden ratio. This sounds a bit complicated, but it really isn't, so don't worry if you have no particular knowledge or insight on all this. As always, we're going to take things step by step and in simple terms. Before we begin, please take a minute to like this episode, comment, subscribe, or if you want more of this channel, subscribe to my Patreon page to get advanced releases, news, downloads, all episodes with background sounds, and more. There is a link in the description and the first comment. It costs whatever you want, from $1, £1, or €1. You decide what you wish or can pay for it. And now, let's get started. I mentioned hexagons before, so let's take this particular pattern as an example and ask ourselves why they form spontaneously in very different situations in nature, to what logic, what underlying force, what need does this correspond. An example that comes to mind when thinking of hexagons in nature is honeycombs. Why do bees build hexagons when they arrange their nests? Actually, they don't really build hexagons. It is not like they have some instinctive knowledge of geometry. The cells they build with wax are roughly circular at first. But wax is malleable, and the bees produce heat with their bodies and intense activity in their hive. This heat softens the wax, and the circular cells adopt this hexagon shape naturally. Why is that? Because when soft or fluid structures pack tightly, different physical and mathematical principles come into play. A balance has to be found between these small cells, these small structures that compete to occupy a space. So an equilibrium forms, an equilibrium in which the surfaces, the walls of these structures will meet with equal force, because that is what allows stability and minimizes energy. We will talk a lot about this energy minimization principle tonight. So, what is it? It is a simple idea from nature and physics. Things naturally settle into the lowest possible energy state. That is to say, the most stable or relaxed or comfortable configuration, because this means less stress or tendency to change. For example, imagine a ball rolling down a hill. Of course, it keeps going down until it reaches the bottom. In physics terms, the bottom of the hill is the point with the lowest potential energy. And systems in nature do something similar. They roll like this ball, metaphorically. They tend to move to arrangements where energy is as low as possible. The processes behind this are various. Different factors are at play: heat, surface tension, gravitation. But in countless configurations, from the very small scale of atoms to the cosmic scale, this principle of energy minimization is verified. To say it differently, nature likes its comfort. It tends to adopt the most comfortable configuration, one that will be stable without spending more energy than necessary. So, returning to our honeycombs, the hexagonal shape there is the one that minimizes energy in a situation where cells are tightly packed. The cells get packed without gaps or waste. There is no space left between them, no space available to occupy that would make the system unstable, able to continue to evolve. And the forces between the walls of the cells are equalized by this hexagonal shape. The limits, the boundaries of malleable structures that are packed are pulled toward these 120 degrees angles due to the energy minimization principle, and also surface tension. We will come back to this phenomenon. Because it is this arrangement that allows to reach an equilibrium. Now we could ask ourselves, hexagons effectively eliminate space between cells. But why not squares, or rectangles, or triangles that could also be packed tightly without gaps between them? Here again, it is about energy minimization. Sharp right angles of 90 degrees are very rare in nature, and generally we have curvier shapes or geometric figures with more sides, because these are better at maximizing the area to perimeter ratio, which means you can have the most space for the least wall length. if squares replaced hexagons in honeycombs, that would require more wax for the same surface, because there would be more walls. Having hexagons instead of squares saves about 7 to 10% of wax for the same storage space and structural strength. So as you see, this hexagon pattern is not a random quirk. It is very efficient in physical and mathematical terms. Hexagons save material. And this is not all. I told you the bees made roughly circular cells with wax that turned into hexagons due to pressure from neighboring cells and surface tension. It is also more energy efficient to evolve from circle to hexagon than from circle to square. It requires less modification of the walls. And for these reasons, hexagons are like a sweet spot. In terms of evolutionary biology, efficiency and sweet spots are always advantageous. They tend to give an energy or resource edge to species. So the fact that bees, and certain wasps too, have perpetuated this shape for millions of years also has to do with the benefits that it gives them. Saving wax means more time and energy available for foraging, making honey and surviving. It is believed this is how physical or mathematical rules can end up shaping animal behaviors, morphology, and instincts. And this is true on different scales. Let's take another kind of natural hexagons, but bigger. The ones that appear in basalt columns. You have certainly seen these, at least in pictures. Geologic formations around the world where stone is arranged into regular hexagonal pillars, stuck together like cells in a honeycomb. Famous sites with these include, for example, Giant's Causeway in Ireland, or Devil's Postpile in the US, it's in California. Why do these appear? These formations were flows of lava at first in the distant past. When lava cools down slowly, and first from the parts that are exposed to the air, so the top and the sides, tension, stress grows inside the lava flow. It does not cool down evenly. So to release that tension, cracks are going to happen. And if the cooling is slow enough, the cracks that release the inner tension inside the lava flow are going to happen at 120 degrees angles, precisely because this is the angle that minimizes energy per crack. These cracks propagate into hexagonal networks. This only happens in the right conditions. Of course, all lava flows did not cool down into basalt columns. If the cooling is faster, the cracks are going to be more chaotic and on a smaller scale, so columns will not form. Yet another example of hexagons is snowflakes and ice crystals in general. The same principles of physics are at play here, but on different materials. Why do snowflakes have 6 branches, 6 arms? because of the way they form when water freezes. When water molecules freeze, they bond in an hexagonal lattice, the way oxygen atoms in water molecules link to others via hydrogen bonds creates a symmetric structure. This is on a very small scale at the molecular level, but however tiny it is, it forces the ice crystal to branch in 6 directions. In a snowflake, this repeats millions, billions of times, and the bigger structure, that is the snowflake, containing millions of atoms, retains the hexagonal pattern. It doesn't mean every single snowflake is identical to others. It is not the case. Depending on the environment around it when it forms, especially at what speed, which depends a lot on temperature, there are going to be tiny variations during growth of the crystal. And this is what gives snowflakes their uniqueness, even though they have the same hexagonal structure. There are other examples of natural hexagons. The last one could be the eyes of insects. You know that living organisms on Earth that have a sense of sight have not all acquired the same types of eyes. Humans, as well as other vertebrates, birds, fish, mammals, have what is called single-chambered eyes or simple eyes. These eyes work like a camera in that they contain a single lens that focuses light onto a single retina, a layer of cells that are light sensitive, and the information received by the retina is transmitted to the nervous system and the brain. This type of eyes is good at forming a sharp and unified image. But insects, crustaceans, and other arthropods do not have eyes like this. They have compound eyes. These eyes are made of many independent units called omatidia, and each of these units is like a mini eye with its own light receptors. The brain combines the mosaic of small images from all units into one big picture. These compound eyes have a lower resolution than camera eyes. Their range is shorter too, but on the other hand, they allow a very wide field of view, often nearly 360 degrees. Many insects can see everything around them or close. And these eyes are also good for motion detection. It is believed these compound eyes evolved by duplicating and clustering simple photoreceptive units that together form an efficient organ. And this implies that good compound eyes pack as many light-sensing units as possible, without gaps between them. And for structural strength and energy minimization, they are going to be hexagonal too. A very different situation than honeycombs or basalt columns, but underneath, it is the same physical imperatives that are at play. So the eyes of bees or dragonflies that are proportionally huge relative to the size of their bodies contain thousands of hexagonal units of facets that are at the same time structurally sound, thanks to the hexagonal pattern, and provide very wide-angle vision. So, as you see with these examples, hexagons keep winning in nature because both physics and evolution reward stability, efficiency, and minimal energy waste. Said differently, in different situations, hexagons are a sweet spot kind of shape. But it is far from the only one. And another type of pattern that we are accustomed to is the spiral. From larger to smaller, think about galaxies first. Not all of them, but an estimated 60% of galaxies in the universe are spiral galaxies. The Milky Way is one of them. They form spirals that rotate around a very massive galactic center, made of a black hole and many stars around it. Hurricanes and cyclones also adopt spiral patterns, and so do seashells, and it is less obvious, but it is also the case for plants. Leaves and seeds on many plants are arranged in spirals. Animal horns as they grow, or plant vines are other examples. And there are also many that are invisible to the naked eye. Microscopic structures, such as the double helix of DNA, which consists of intertwined helices, the structure of many proteins, or the bodies of some bacteria. One thing those natural spirals have in common is some kind of movement. It can be fast movement, like the rotation of galaxies or tornadoes. It can be slow, when it is growth or diffusion. But nature tends to prefer this shape when there is movement. Why is that, and what are the characteristics of spirals? In essence, spirals are a preferred shape because they are a path of least resistance for growth and motion. We are back to energy minimization, but this time with movement. And I mean movement in a broad sense. When it comes to animals, the spiral shape has advantages for animals that grow shells, or for plants that grow leaves and need exposure to sunlight. Let's take the example of seashells. They are built by mollusks that live inside them and that are soft-bodied. The shell gives them structure and protection. They could get that from a random hard structure, or a tube, or another shape if you think about oysters or mussels. These happen in nature. But many species of mollusks have evolved to make coiled shells, because these are advantageous. As the organism grows, a spiral-shaped shell keeps the shell proportional and strong. A straight tube or an oyster shell is strong on a small scale. But the larger they become, the more fragile they also become. They could break. The same way that a long stick is easier to break than a compact piece of wood of the same mass. Mollusks that grow shells have what is called a mantle, a tissue layer that secretes the shell material, generally calcium carbonate, that is filtered in water or taken from their food. This mantle continuously adds new layers of shell material at the opening of the shell, and only at the opening. As the animal gets bigger, it needs a larger living space, so it builds a wider rim, and following this expanding opening, the shell grows regularly. It doesn't make a bigger version of the old shell, it expands it by attaching new growth to it, new material, at an angle to the existing part, an offset angle. This angle stays roughly constant relative to the direction of growth, and that is what creates the spiral. Here again, efficiency is key to understand why. This shape optimizes the strength, the resistance of the structure for a given quantity of material and energy to spend on building it. If we thought theoretically, a sphere could make more sense for the shell of an animal. This is the shape that could be equally strong whichever side you attack it. A sphere distributes stress evenly, and it would optimize the space inside for a given quantity of material. But a sphere could not accommodate the growth of the body inside. It would have to be remade every time the mollusk outgrows its shell. So the spiral shape of the coiled shell looks like an optimum of resistance and material and energy usage for an organism that needs to grow and stay protected all the time. Now, how do so many mollusks, marine or terrestrial, if you think of snails, for example, know how to build a spiral? They don't, in the sense that they have no brain planning or deciding the shape like an engineer would. The spiral emerges from a combination of instinct, of built-in biology, that is to say, genetic development that evolved over millions of years, and of feedback from the animal's body. It builds the shell depending on its needs for space, following a hard-coded process. It could be compared to our fingernails or our hair. They grow constantly, but it's not something conscious. Without us giving it any thought, our fingernails expand mechanically, always in the same direction, as our hard-coded biological processes are at work. The shell of a mollusk grows the same way, without the animal giving it any thought. And yet they form spirals that, because they have an angle, are remarkably constant. They are called logarithmic spirals. What does it mean, logarithmic spirals? Not all spirals are the same. For example, if you think about a roll of measuring tape or a roll of paper towels, these form spirals. Spirals with the same spacing between each turn, these are called Archimedean spirals. A logarithmic spiral is one with a curve that expands at a constant rate relative to the angle of rotation In other words, if we draw a line from the center of the spiral, the angle between the spiral curve and this line is always the same. Think about a snail's shell. Each turn is wider than the previous one, but the angle is always the same. And this is what gives the spiral this orderly expansion pattern. Now, this brings us to two things that you may have heard of: the Fibonacci sequence and the golden ratio, at the junction of mathematics and art or aesthetics. The Fibonacci sequence is basically a series of numbers where each number is the sum of the two previous ones. So it goes like this. Typically it starts with 0 and 1, and then the number after that is 0 plus 1, so it's also 1. After that, 1 plus 1 equals 2, 2 plus 1 equals 3, 3 plus 2, 5, 5 plus 3, 8, 8 plus 5, 13, and so on. Then we have 21, 34, 55, 89, 144. This sequence has been observed in nature, not always exactly, but very close, for efficient packing especially. For example, in sunflower seeds or pine cones. We will come back to this. Now the so-called golden ratio is a ratio, a number, formed by the ratio of successive Fibonacci numbers. 55 divided by 34, 89 divided by 55, and so on. This number is not perfectly stable because the Fibonacci sequence does not expand at a fixed rate, meaning that each Fibonacci number is not the previous one plus a fixed percentage. So the golden ratio is defined as the limit that the ratio of successive Fibonacci numbers approaches as they get larger. Its value is about 1.62, precisely 1.618 and a long series of numerals after that. Now the reasons why you probably heard of this term, golden ratio, is that since the Renaissance, and based on the observation of natural spirals and the Fibonacci sequence, many artists, architects or designers have used it in their work, assuming that it helps produce pleasing and balanced compositions. Da Vinci referred to it, and the concept had a surge in popularity in the 20th century. The underlying idea here, which makes the golden ratio seductive conceptually, is that it would be a kind of universal law or force in nature, a principle that would unify a bit of everything. Mathematics, biology and life, physics, our sense of aesthetic, of beauty, maybe because we belong to the cosmos, and our minds and emotions would be drawn to it. It's a kind of holistic mix, a concept that evokes or promises perfection, which makes it intriguing. But is it real? It's hard to tell because it is not as if beauty or balance could be measured on a calibrated scale. these are subjective experiences. It is true, however, that approximations of the golden ratio in pictures or architecture tend to be liked rather universally. An example of this is the rule of thirds in photography or in paintings, a rule that many painters of the past centuries followed in landscapes, for example. It translates into 2/3 of sky in the upper part of their pictures, and this kind of proportions seem to make visuals flow and focus more naturally. So there's probably something here. But respecting exactly the golden ratio never seemed to be a guarantee of success. On the other hand, many works of art or buildings that ignore it are judged as beautiful or balanced as others that follow it. And where things fall apart a little bit is when we search for the golden ratio in nature, which was supposed to be the main argument that made it an universal principle. In reality, the golden ratio is almost absent in spirals and other patterns. Some natural shapes approach it sometimes, but that could well be a coincidence. Because, for example, the systematic study of real shells of many mollusks or the growth patterns of many plants show different ratios of expansion, 1.2, 1.3, 1.4, generally less than the 1.62 of the golden ratio. And this is why the golden ratio could well be more of a popular myth. It's not a number that nature seems particularly interested in. It does not correspond to physical laws that would be reflected in matter, and it has no use in geometry, like the number pi, for example. So, the golden ratio is probably to be taken more as something inspirational, maybe a tool for artists and designers that seek balance in their creations. But it is still approximate, and not really the kind of universal principle that has been believed in the past. If it was, we would be able to find it in nature, but we can't. Maybe what this could tell us is that we have a tendency to look for intentionality or a form of conscience in nature. The idea that nature would follow math consciously, a language we can understand, is attractive. It gives the impression that there is an universal language of the material world, an intentionality out there that we could decipher and reach the knowledge of everything physical thanks to it. But maybe this is just a belief, and it works the other way around. Mathematics describes the results of natural laws, of physics. It is an extraordinary tool, but it does not necessarily dictate them. A language, however powerful it is not a will. So now let's go back to our natural spirals. I told you shells were an example, but there are many others, obeying to different constraints. On a much larger scale, there are galaxies that are spiral-shaped. Not all of them. About 60% of galaxies would be like that. with the majority of their stars placed on arms around the galactic center. The other types of galaxies are elliptical, that is to say, roundish, oval, but without arms, and a few ones are irregular. They look messy with no clear structure. This is believed to often be the product of recent perturbations. These galaxies are often smaller and could have been perturbated by their proximity to other galaxies fairly recently. In cosmic times, it can be millions of years, so they wouldn't have had the time to reorganize yet. We think many galaxies form and maintain a spiral because they are disc-shaped and they have significant rotation. They conserved this rotation, in physics terms this angular momentum, from their formation history. Now they also have regions of higher density of stars and star systems, forming these arms that branch out of the galactic center. The most accepted explanation to this is that it would be due to the fact that regions with a higher density of objects tend to orbit slower than individual stars or gas clouds. So the arms would be a bit like traffic jams, regions where stars and their satellites would slow down a little. So they are packed more densely than in between the arms. The distances between stars are still mind-boggling, several light years, but it is less than in between the arms. And the arms would also appear brighter, because with the higher density of gas clouds, of nebulas inside them, there would be more new and brighter stars forming there. So the spirals here are a direct product of motion, of rotation. And on a much smaller scale, this is what happens with twisters, hurricanes and cyclones. Their shape minimizes energy loss by friction in the atmosphere. Here again, it is the path of energy minimization, which allows for more efficient wind flow and heat release. The very same minimization principle that shapes different plants as they grow, together, in this case, with optimization of their sunlight exposure. What does it mean? If you look at sunflower seeds, for example, at how they are arranged at the center of a sunflower, you will see that they are not just aligned. They are placed in interlocking spirals, which are not always but often 34 in one direction and 55 in the other, both consecutive Fibonacci numbers. This arrangement packs hundreds of seeds tightly and at the same time exposes them to light and insects, pollinators efficiently. The same type of spiral arrangement, also with Fibonacci numbers, is found on pine cones. Typically, they present 8 scales one way and 13 the other way. This is also a Fibonacci pair of numbers. This arrangement protects seeds and gives each of them about the same chance to be dispersed by wind. Yet another example in plants is the structure of cauliflowers. The entire head of a cauliflower is made of smaller cone-like spirals that repeat at every scale. They are fractal-like. What is a fractal, by the way? It is a shape that looks roughly the same at any scale. Meaning, if you zoom in or out, you see similar patterns repeating over and over. So, for example, a tree, when it grows, tends to follow a fractal-like kind of pattern. The main trunk splits into branches. Each branch splits into smaller branches, and each twig splits again. We get a complex shape and an infinity of variations. There are no exactly identical trees. By the repetition of the same pattern, the same rule, over and over. With of course small variations due to the tree's circumstances, its environment, the wind, the soil, its position to the sun, other neighboring trees. And actually many trees, like oak, beech or some palm trees, also follow a spiral development as they grow their branches and leaves. The spacing between them reflects Fibonacci ratios, 2:5 or 3:8. And this maximizes exposure to light, especially for lower branches and leaves. As the tree grows taller, it avoids excessive overlap. With all these examples in plants, it is important to remember that the spiral shape and Fibonacci numbers happen and are hard-coded into their genes. But this is not an absolute rule. Plenty of plants do not grow or place their leaves in spirals. Yet they existed like that for millions of years. And this is believed to be because the spiral is an optimization followed by nature. But it is not really a rule that would govern the living. The reason why these plants I mentioned retained their characteristics is like for mollusks that build spiral shells. It would give them an advantage in evolutionary biology. And so generation after generation, individuals with this advantage would have been selected. They would have thrived within their species. And this pattern would have come to dominate the genetics of their species. But this is not a condition for plants to survive. There can be other advantages, other strategies. And as I was mentioning fractals, the repetition of a same shape on different scales, this is another type of pattern that nature often forms. Not just for plants like trees or cauliflowers, snowflakes also have fractal edges, clouds too. When we look at them, we may see a blob that looks random and just shaped by the wind or atmospheric conditions. But clouds are made of puffs that tend to be self-similar at multiple scales. Or lightning bolts, another example of fractals. These are very ephemeral, they last a fraction of a second. But the main bolt branches into smaller forks, which branch further. And again, it is believed to be a consequence of energy minimization and natural optimization. For a lightning bolt, which is an electric arc, an electric discharge, the fractal pattern is the easiest way, the easiest path through air. Why is that the easiest path? Because after all, the straight line looks easier, and bolts could be just columns between clouds and the ground. It is because air is never uniform. It has slight variations in density, humidity. There are dust particles in it, ions, differences of temperature. And these create tiny differences in electrical resistance. Depending on where you are in a column of air, electricity will travel more or less easily due to these irregularities. So when a lightning bolt appears, it is because there is a difference in electric potential, in voltage, between a cloud and the ground. Electricity tries to flow to neutralize it, to even out the potential between these 2 points. In other words, there is an excess of electrons in the cloud that is drawn to the ground to even things out. If the air was perfectly uniform, this flow would take the form of a straight line, because this is the shortest distance possible, and as we have seen, nature keeps things as simple and energy efficient as possible, energy minimization. But the air is not uniform, so when the flow of electrons starts descending from the cloud, it seeks the path of least resistance. At each step, it branches out in multiple directions, like fingers reaching out, and it chooses the direction where the air is easiest to go through, to ionize. Once one branch gets close enough to the ground, the whole channel lights up brightly, and we see the bolt. In short, the fractal shape with all these subdivisions is not random. It is rather the smartest or laziest path electricity can take through imperfect air, always picking the easiest next step in what is like a branching contest. This is why lightning bolts look like glowing trees upside down. And returning to plants, why repeat the same structure over and over on different scales? Why the fractals? Because when you repeat growth rules or physical processes, you can get high complexity with limited instructions, limited genetic or physical instructions. It is efficient resource and energy use. And at the same time, an arrangement driven by a fractal pattern is good at maximizing exposure to light and nutrients. It is like a hack. Again, that's the lazy or smart way of getting the most from limited resource. And that is a huge evolutionary advantage that seems to have been retained by many plants, from tree branches and roots to most green leaves on plants that need sun exposure. One of the most obvious examples here is ferns. it is easy to see if you inspect a firm branch. Each large frond branches into smaller leaves that mirror the whole shape, and then those into even tinier ones. The fractal branching maximizes sunlight capture and minimizes overlap, which is vital in the often shaded forests where ferns grow. I told you that fractals repeat the same pattern over and over, that in some cases it was the path of least effort, and like for other shapes we talked about, hexagons or spirals, they stem from a principle of efficiency. Yet, when we look at nature on different scales, from a galaxy to a forest, things look way more messy or random. There are no two exact places that are the same on Earth. Even snowflakes are all different. So that seems paradoxical. There are patterns, there are rules of nature that lead to certain favored shapes, yet nature looks incredibly chaotic or creative. It does not repeat itself perfectly. So how do we reconcile these two realities that seem contradictory? This is where we need to talk a little bit about chaos theory. What is it, and why does it relate to our topic? Chaos theory is a branch of science and math in particular that studies complex systems that obey to certain rules. The rules of physics are impossible to get around. Yet they can produce widely different outcomes. There is order underneath, yet very different outcomes. An example of it that is often given is with weather forecasting. We know the rules of weather. These are physics. But tiny tweaks to a system, like a butterfly flapping its wings, may snowball into big events like a storm somewhere else. The idea is that tiny changes in starting conditions can lead to very different outcomes. That's the meaning of this so-called butterfly effect. But however big the consequences of a small variation on a system, the system still tends to return to converge to certain patterns. Hurricanes are an example of that. They may be the product of a tiny change in starting conditions that will snowball and lead to very turbulent airflow. But they still return to the spiral shape every time. Why does a change in starting conditions lead to such different outcomes? Because a chaotic system is highly sensitive, so sensitive that even something very small may end up mattering a lot. The system is so touchy about the exact starting point, and this starting point so hard to perfectly know, because there is a very large number of factors, that it becomes unpredictable. In theory, if we could measure the start perfectly, not leaving aside a single factor, however tiny, we could predict the outcome. With gigantic and perfect capacity of modeling and calculation. But in practice, it is impossible, too complex. This makes the system less and less predictable in the future, as tiny changes have the potential to repeat and snowball. The difference between a simple and a chaotic system could be illustrated with the example of the ball running down a hill that I gave you earlier. If we see it as a simple system, where only gravity matters, and the hill as well as the ball are perfectly regular, and we try it in a void, a small change in where we start rolling the ball will only make a small difference at the end. This is predictable. But reality is not like that, with a perfectly known set of conditions and a single force at play. An example of real, chaotic system could be if we take a real hill surrounded with real irregular air, and we pour water that will trickle down to the bottom. In that case, even a super tiny change, like starting 1 millimeter to the left or to the right, may grow and grow over time as the water falls down the slope, and lead to very different flows, one following a calm path, for example, and another one following a wild path. It is not the rules that are different or random, just the starting point, and our inability to perfectly know it. And this is how nature, chaotic processes, can create all these repeating but irregular patterns we see, that are unknowable in advance to us. Yet, underneath the mess, there are still patterns like repeating shapes or what is called attractors. These are patterns of efficiency that the system will tend to converge to, and that gives some predictability on a larger scale. For example, if we take a galaxy, the way billions of stars and their satellites are going to travel in space, and their orbits are going to be altered by a multiplicity of tiny factors, this is unpredictable. It is a chaotic system. Yet we can predict that they will end up forming a spiral with arms, because this shape, this natural shape that stems from principles, is an attractor, a form the system will be drawn to. Of course, when mathematicians start modeling all of this, it becomes incredibly complex and rich. It also has direct applications. Think about weather forecasting, for example. But these are the basic principles, and they explain why a limited number of laws of physics, chemistry, biology, acting on a limited number of chemical elements, can lead to such a diversity of shapes, of arrangements. These are highly sensitive systems with not an infinity but a very large number of factors. There are other recurring natural shapes we could talk about, like meanders, cracks, tiling. But to conclude, let's go back to the animal kingdom and talk about another type of patterns, stripes and spots. Think about zebras or tiger's bands, or the rosettes on a leopard. and on many species of fish, the dots on a ladybird. Why are different animals covered in these patterns, instead of having a single color, or show smooth transitions between colors? If we approach it from the angle of the advantages these patterns provide, we can find some. They can be used for camouflage, they make them hard to spot, or warning, or to attract mates. They could also help temperature regulation. In the case of zebras, for example, their stripes create mini air currents between the black parts that heat up more under the sun and the white parts that heat up less, helping cool the skin. So it is understandable why evolution may have selected these traits. But how and why did they actually form? That's where, again, physics and math come in. Just like for the energy and resource efficient hexagons or logarithmic spirals, here again we have a self-organizing process where during the development of embryos, two chemicals spread and interact. Animals with colored patterns produce two substances, one that is called an activator, that promotes pigment, and one called an inhibitor, that stops it. In a process that is unpredictable, because it is chaotic, highly sensitive, and with many starting variables, the two substances spread around the individual's body. And in some locations, the activator wins, so there will be pigment there, whereas in others, the inhibitor dominates. There will be blank space or a lighter coloration. So again, here we don't have a predetermined blueprint saying each leopard will have a dot in a certain place, or each tiger a stripe there. They will have these patterns because the production of the activator and inhibitor are hard-coded. But each individual is going to be different because of the circumstances, of the tiny differences becoming bigger over time in the chaotic system that is the spreading of the two chemicals over its skin. And here too, we have energy minimization in action when the chemicals spread. Having them mixed in the same places would create tension and energy waste as they cancel out their mutual effects. So instead, the system eases, relaxes into a pattern in which they are separate. The system that will use the least energy, like for round cells in honeycombs, settling into hexagons, or lava cracking into hexagonal pillars as it cools down. Just the same simple rules repeated and creating complexity and uniqueness. This is the end of our story for tonight. We have barely scratched the surface of it, so I encourage you to look for more information if you are interested in this. If you are not sleepy yet, you can pick another story from my library and embark on another adventure. Or you may close your eyes, let go, and fall asleep. I'll be back soon with a new story. And in the meantime, sleep well. Au revoir.